and welcome to Organic Chemistry. First, it's good to talk about some of the fundamentals. So, it's important to recognize that, as it says on the slide here, atoms make up everything. It's kind of a punchline of a dad joke, but it's a truism of chemistry. But let's first look a little bit about the makeup of atoms. So again, as a reminder, the nucleus of the atom is made up of neutrons and protons. And around that, there are electrons. So for example, right here is shown an example of helium. You notice I put a helium-2 here. That's the isotope of helium. So when you look at the periodic table, and we'll look at that in just a moment, we will see all of our elements displayed with a number at the top, like 6, and that's the atomic number. The atomic element symbol, in this case carbon, C, is shown in the middle, and the atomic mass is shown at the bottom. And the mass is really the protons and the neutrons added together, and it's a sum average of the various isotopes that are naturally abundant on Earth. I'll point out that this mass also includes the electrons, but those are very, very small compared to everything else. So when we look at the periodic table, this is really our best friend as a chemist. And the things that I want you to look at in class, or keep a mind of in class, is that these the various periods in the table, they tell us about the reactivity of the various atoms and elements that are in the periodic table. We'll also be looking at periodic trends on the table, such as electronegativity, which we'll talk about later, where I'll just, spoiler alert, tell you right now, the trend is that you go from less electronegative on the bottom left to more electronegative in the top right. So it's important to understand that in organic chemistry we will be talking about orbitals, and orbitals are places where electrons go. There's only a certain number of spots per level, that's 2, and there can be 2 electrons per orbital. And it's important to also recognize that the shapes of these orbitals, that you've probably seen some of these shapes drawn out before, but they're really probabilities of where the electrons might be. The electron's not here or there, it's kind of some average over a cloud of locations. So we have s orbitals, we have p orbitals. S orbitals are kind of a sphere shaped. P, I like to think of them as peanut shaped. And let's look at carbon, for example, where there are 6 protons and 6 electrons. And the nice thing about the periodic table, again, is it tells us, based on the atomic number, how many protons are found on an element, and therefore how many electrons are found on the element when it's neutral. So the first thing to recognize is that 2 of these electrons happen to exist in a closed shell. That is, that it's the first row, and it effectively looks like helium. This closed shell we can think of as helium. And now the interesting electrons, the ones that we really care about and focus on in organic chemistry, are the valence electrons. So these valence electrons are on the outermost orbitals, and they are the reactive orbitals. I'll also point out at this point that the p orbitals, there are 3 of them, and these 3 p orbitals are orthogonal to each other, so they're 90 degrees oriented from each other. There's one in this plane, one in this plane, and one in a plane coming straight out from me to you. So when 2 atoms meet, they bond, and we'll talk more about bonding later, but let's just look at hydrogen as an example. So each hydrogen atom has 1 electron that it can share. In this case, I've highlighted their colors as red and black, but really, once they are sharing them, they have no idea what electron they started with. And so we often draw these are atomic orbitals here, and they form molecular orbitals when 2 atomic orbitals interact. And so when these 2 electrons interact and form a bond, that bond is more stable than if those 2 electrons were not bonded, and that's why they bond. We'll talk about that again later. And we call this a sigma bond. So let's look at the example then when things don't necessarily work out. For example, helium, a noble gas, doesn't bond with really anything, and it certainly doesn't bond with itself. And at first pass, you might say, well, hey, look, it's forming this bonding orbital. One electron from each of these helium orbitals can interact and form a bond. But the key thing to look at as well is that the remaining electrons that didn't go into this bonding orbital are left around, and they form an antibonding orbital. The antibonding orbital is actually there's a greater amount of energy that would be required to put the electrons into the antibonding orbital, and so they end up canceling each other out, and helium just goes about on its merry way as helium with 2 electrons. It's important to recognize in organic chemistry as well that there are antibonding orbitals, there are antibonding orbitals present even on a molecule like H2, but they are simply not populated. If they were populated, they would break that bond. So the antibonding orbitals, you can think of it as the place where you would go if you were to put the next electron there. Another way people sometimes like to think about this is if you're in a building, just because you're not occupying the lowest level of the building doesn't mean that there aren't floors to occupy above you. So let's briefly now look at some of the bonding that happens with carbon. After all, we are in organic chemistry, and carbon is the currency of organic chemistry. So carbon has 4 valence electrons, as we looked at earlier. And so if there are 4 hydrogen atoms that each have 1 valence electron, there can be 4 hydrogen atoms that can bond around carbon. And in this case, this is the Lewis structure shown here, named after Gilbert Lewis. And you've likely seen the structure before, but really organic chemists seldom use Lewis structures. We often go to the next level where we represent the electrons that are being shared as a bond as simply a line. And so this line bond structure is another common way we as organic chemists can show structures, but you'll see in just a moment that this takes too long to write out, and so let's say ethane doesn't take very long to draw out, but once you get to propane, just 1 carbon added to that, it starts to take a while to simply draw that molecule. And so organic chemists simplify this with a shorthand like that, where each edge corner is a carbon, and the ends of these are also carbons. And we'll talk a lot more about this as we go on in class. But let's briefly go through the different number of carbons just for a nomenclature perspective. And I'm not very heavy on nomenclature in this class, but I do want you to know the carbons 1 through 10 because they come up over and over again, and as I talk about them in class, it's going to help you if you know these names. So if you look at the number of carbons, the name, prefix, abbreviation, and how it's drawn. So first, as we talked about before, is methane, and we call that methyl. We abbreviate it as ME. Typically we'll just draw out CH4, or if there's a methyl group at the end of, or bound to something else, sometimes we'll just have it as the end of the line. Now this squiggly line that I drew here, this squiggly line here, that's often used to denote that that whatever is over on this side could be really anything else. It just gives you a lot of openness there. So if we have two carbon systems called ethane or ethyl or ET, and we simply draw it as a line. So again, each of the two ends of those lines represent a carbon atom. If we go one further, we have propane or propyl or PR, and again, this is where we start to add some angles to our line drawing, because we now have 3, and we'll talk later about why we draw the angles the way we do. 4 carbons is butane, like you might have in a lighter, for example. Propane can also be found like in a propane tank. These are these compounds. Butane is represented as butyl or Bu, and now we have this 4-carbon chain drawn. If we go to 5 carbons, it's pentane or pentyl. We often don't abbreviate pentane. Sometimes we might write pent or something like that, but it's not as common an abbreviation as MET, PR, or BU. And then going further down the chain, we have 6 carbons being hexane or hexyl, 7 being heptane or heptyl. And then, just very briefly, we'll go through the last higher numbers. Octane for 8 with octyl, 9 is nonane, nonyl, 10 is decane or decyl, and then for those who really like to go to higher numbers, which I will not ask of you, 11 is undecane, 12 is dodecane. And that's it for today's class. Thanks. Bye.